Good afternoon. Let's get started. Thank you all for coming. I'm very honored to welcome Professor Krish Sharman from UMass Amherst as our speaker today. Professor Sharman's academic journey took him from IIT in India via Canada to Michigan, where he received his PhD in marine engineering and naval architecture, both things. I think all of your degrees have something with ocean engineering, marine, naval architecture. And he then worked in Australia in academia for about 15 years before moving to Maine to work on offshore wind there. And more recently, a couple of years ago, he then moved to the University of Massachusetts, where he now is the endowed chair for renewable energy in the Department of Mechanical and Industrial Engineering. So without much further ado, okay.
Thank you very much, Martin. It's a great pleasure to be here. I've been traveling between Maine and Massachusetts a few times, and so now it's a nice stopover in the middle to talk to people with similar interests as mine. So great to see the ocean engineering program growing at UNH, and I was very pleased to hear about the progress that's going on and see all the students who are part of both the graduate and the undergraduate program here. That's wonderful. So I thought I would talk a little bit about mooring systems today and talk about floating installations, both applied to offshore oil and gas as well as to offshore wind. I'll give a very brief on our research group at the University of Massachusetts and what areas we work on. Those are the three areas we are very interested in: offshore wind, marine hydrokinetics, both wave and tidal, as well as then coastal aquaculture systems. And a lot of my effort these days are in building this wave current laboratory, which is not like as large as the Chase facility. It's about a 11-meter length facility, but we are very keen on developing a good understanding of waves and currents, and we see that as the next big challenge with marine hydrokinetic systems. So that's kind of the layout. As you can see, there's some dimensions there. It's about 1 meter and 1.2 meters wide and operating water depth of 1 meter. We want to equip it with photography and PIV systems, and we also have in our team people interested in numerical simulation. So all of these we hope will come and support us in the three areas we are working on. Some of the topics we are working on in these areas in offshore wind. Our recent research has been focused on how the platform works in the environment. What sort of loads does the environment, both wind loads and wave and hydrodynamic loads that are imposed on the platform, how to simulate these extreme environment, what sort of flow-induced vibrations that we might encounter, and of course mooring systems, which is a real kind of thorny issue for the emerging floating offshore wind area. Interestingly enough, even though I'm part of the Wind Energy Center there, most of my funded work is actually in wave energy. And as you see here, some of our projects with the National Renewable Energy Labs, they have this flap type wave maker wave energy system, and we did some tests in Maine on this device. The novelty of it is it has little shutters you can open and close, and the idea is you can shed loads during the most extreme condition. And now we are working with NREL on a system that's not bottom mounted but slightly lifted from the bottom, and as you can see in this picture here, so it's a little tower and it's sitting on top of that. So we hope we'll be able to test it in our new facility at UMass from this system. We have also supported a local company in Massachusetts, which has been working on an eccentric mass rotating about the central axis as a way of generating power from waves. So we did some numerical tool development and some experimental support for that. We have also, in the past, worked with Virginia Tech on some of their point absorber ideas, and I have a personal interest in oscillating water columns, having worked with them from even from the time when I was in Australia, recently looking at floating oscillating water column systems. And also there is that interest in seeing how hybrid wind and waves can come together. So can wave energy and wind energy coexist? And if so, how can it be made economical and stuff? The food, energy, water nexus and the aquaculture idea has very strong social implication. And as many of you can understand, our engineering solutions these days should be socially sustainable, social engineering combined with technical engineering, if you will. So aquaculture systems have a very kind of community focused aspects to them. Our engineering is looking at how can we ensure safety of aquaculture infrastructure. And in particular, we are interested in mooring systems and the ropes they use. And I have also extended support to the ARPA-E programs when they did the large-scale macroalgae production. And I know UNH is involved in it in a very big way in the Mariner projects. We also have I have a student who was working on better prediction models using SPH, smooth particle hydrodynamics. Let's see if I can get my mouse to work. Actually, like this one. Let's see if I can do this. So these are like SPH simulations of objects moving in water. The idea is to see if we can come up with better mooring line models that can also be integrated into this simulation. And I'll touch upon this towards the end of the talk on some of the viscoelastic and viscoplastic modeling of synthetic mooring lines and how we are working on developing that. Also did some supporting work for NOAA for their mooring system guideline development. A couple of things I'll mention in the service area is I also contribute to the ASME's Ocean Offshore Arctic Engineering Conference, and I'm the coordinator of the Renewable Energy Symposium, the OME conference that happens every year. We also have a new conference on offshore wind. It's called the International Offshore Wind Technical Conference, and the next one, that is 2020, is going to be in Boston, end October this year. So an open invitation for anyone interested. Okay, so I want to start. I have two parts. I'm going to see if I can, how much justice I can do to both of these parts in the limited time. I'll start with part one, which is focused a little bit on the oil and gas side, but it also kind of leads you into what are the challenges we are facing with the floating offshore wind side. Just to get everyone on the same page, when we talk about how moorings influence a platform motion, in conventional naval architecture, we have the vertical plane motions, heave, pitch, and roll, and you can see how those motions come about in that diagram there. The vertical plane motions are called seakeeping motions in naval architecture, and in offshore engineering, we call them as global performance. And then the other three motions are called the horizontal plane, which is surge, sway, and yaw. And in ships which are moving forward, these become the maneuvering aspects and the maneuvering parts. And this is in moored systems, these are called the station keeping behavior or the performance of it. So conventionally, we have separated these two motions because they are also segregated from a spectral standpoint. In terms of frequency of the range of frequencies, these two motions are separated. That's the way they occur naturally. And the mooring systems are primarily designed to work in the lower three motions. And that kind of gives certain unique advantages. The principal advantage being the horizontal plane loads that are influencing a mooring system are much smaller in magnitude compared to the vertical plane loads. And so you can get away with the smaller mooring system on a thinner line and then kind of make a system robust and ensure its station keeping ability. So let's keep that in mind, and then we'll see how mooring systems, the progressive use of mooring systems actually allows the moorings to kind of move into all these motions, and that's where a lot of challenges arise. So why even have a mooring system? So we have all these mean forces hitting on a floating vessel. And if you do not have a mooring system, then the platform is going to keep moving. And so the mooring system keeps the platform from going adrift. And the dominant influence is on the horizontal plane motions. So these are the three common types of mooring systems that we see in the industry. The catenary system and the spread system and the taut system. The catenary system, the primary, the way the restoring effect works is by, it's basically a change in configuration, which is what gives you the restoring effect. But it's also quite heavy. The spread mooring system, which is a combination of different types of material. This is an example of a polyester system used in an oil and gas installation. And what we have is a chain in the top, and then you have a wire, which could be a polyester, or it could be a synthetic rope or a wire. And then you have a chain at the bottom. So with the semi-taut system or the spread system, there is a combination of tension in the line and the line stiffness together. They provide the restoring effect. And in the case of purely taut system, like the tethers of potential like platform, basically the platform moves, and then it's the change in the direction of the pretension in the line which provides the restoring effect. So when we move from the catenary system to this type of system, what we see is we have this the uplifting effect on the anchoring system. So you got to come up with better anchoring and foundation arrangements for the semi-taut system, as well as in the case of the taut system. So the foundation takes on a much bigger role. It becomes more expensive in all these systems compared to the catenary system, where you can get away with a little drag anchor, and which is one of the cheapest ways of doing it. In terms of mooring line material, the chains are the most common and very kind of traditional, and there are well laid out, commonly available handling systems for chain, but they are heavy, and they are only ideally suited for the catenary type arrangement. And then you have the steel wire system, which is a stranded cable arrangement, or you can also have the synthetic rope, which is a braided structure. What we are finding is the viscoelastic and viscoplastic nature of the synthetic rope can make a big difference in the way the rope behaves. So So I want to initially talk about a very interesting problem, an interesting research we did over the past 10, 15 years now, is looking at the station keeping of a turret moored FPSO, floating production, storage, and offloading system. So here, the mooring line is a very conventional arrangement where we know how the system works, and it's basically in the station keeping domain. And you will see no influence of the sea keeping aspects, the vertical plane aspects. And here we came across a very interesting instability problem, which I'll show some slides on. So for those who are not aware, FPSOs are, as the name implies, they are remotely operated production systems where whatever is produced is processed on board the vessel, and then the hull has a number of tanks where the produced fluids are stored and offloaded every few days when a tanker, shuttle tanker comes in. Many of these vessels have an internal turret arrangement, something that looks like what you see in the picture here, and all the mooring lines kind of go and attach into the turret. So the vessel itself can freely weather vane about this single point arrangement. And in offshore Australia, there are a number of these vessels because the fields are a little bit remote, and having pipelines to bring the produced fluid to shore is simply not possible. So having FPSOs is really a very economical option. But what we found there is, from anecdotal evidence from operators, is the vessel very rarely stays in the weather vaning position. So if there is head sea coming in, the vessel is supposed to align itself in the direction of the waves. But instead, when the sea turns direction, the vessel will simply turn itself so that it's always aligned. At least that's the idea. But what people found was oftentimes FPSOs need extra tug support because it seems to align itself at an angle with respect to the oncoming waves, and that resulted in very large roll motions, consequently affecting processing operations and so on. So we did a research project where we had a good collaboration with the Institute of Ocean Technology in St. John's, Newfoundland, Canada. And while the video is running, I'll talk about this experiment we did. We built a model FPSO, which is basically a converted VLCC, and we put mooring lines at a turret. We put a turret in there, a turntable, put some mooring lines, and then we wanted to first test it in regular waves, just to understand its response amplitude behavior. And surprisingly, what we found is what you're going to see in the video. So we later tested it in random waves. There were no winds, no currents. We had 4 mooring lines. We instrumented them, and you can see something that's happening. The waves are coming from right to left, and what you see is the vessel is not aligning itself in the direction of the waves. It's kind of invariably turning, and it seemed to be very comfortably located at some angle. And in this particular case, what we found was the angle is about 35 degrees with respect to the oncoming waves. So clearly, it's then taking waves beam on or kind of quartering condition, resulting in roll motions, and so that's going to create all sorts of interesting complications. And it also complicated our experiments because if the vessel would not stay in one place, we cannot get the response behavior because the response depends on the angle. So we set about trying to understand why this is happening, and then we came across this. We started hypothesizing, and then what we saw was this heading instability, and this is directly a consequence of 2 types of drift loads. These are basically small loads, small forces from the waves happening at the in the station keeping range, very low frequency. The mean loads creating a low frequency motion. So these are just mean forces and non-linear mean forces. One of them creating a moment about the turret, another one a mean force acting on the hull, and you can see that these two have two counteracting moments, and the angle at which the hull is settling down is simply given by the point where these moments come to equilibrium. And the moment obviously depends on the angle at which the hull is located. So we also did some numerical simulation of this work. It turned out to be a PhD thesis of one of my students. And what we found is if you look at how the equilibrium angle in the y-axis changes with the frequency or the wavelength of the waves, we found something very interesting. That is, up to a certain point, we don't see any changes. The equilibrium angle is 0, which is what we want. We want the hull to be facing the waves, so that's zero equilibrium. And at a certain wavelength, when the wavelength and ship length start at some ratio of 0.5 or so, we start seeing the experimental data pointed out that this equilibrium angle was changing, and like what we saw in the video there, the equilibrium angle was around 30, 35. So it started changing up to a certain wavelength, and then it kind of flattened out, and then it reduced. And we saw the same thing when we did our numerical simulations. We did both. Both frequency domain analysis and also time domain analysis, and our curves kind of also predict a very similar behavior as to what we saw in the experiment. So in one of our papers, we talk about a bifurcation in the equilibrium that results in this behavior, and we studied how this happens and why it happens, and so on and so forth. So when I moved to Maine, we looked at doing another set of experiments with a similar FPSO model. And I helped build a facility at the University of Maine, which is this wind wave facility. We have the wave tank is about 30 meters long, 9 meters wide, 4.5 meters water depth. We had wave makers on one side and a beach on the other end. And we had this wind machine, which was capable of producing quite large wind speeds. And we built a little FPSO model, a replica of what we tested in Canada several years back. And we subjected that to multiple environmental conditions, including regular waves with wind speeds, as well as waves which are bidirectional. And what we found was kind of very reinforcing of what we saw in Canada. We used very similar mooring systems, very lines with the springs in them, which matched the reaction force or the stiffness from the actual mooring system. We have a little turret, a little turntable turret for the hull. And what we found in that case is also the heading angle versus the wavelength to ship length ratio had a very similar behavior as to what we saw in Canada. The no wind case matched with the experiments from before. And when we added wind speeds, also this heading angle changed. Presumably the wind speed adds another moment to the equilibrium, and consequently that affects. So all this were published in a couple of papers there. Then we posed the question, what would happen if an FPSO like this were to be in an environmental condition which has both waves and swell? So it's a bidirectional sea state, which is very commonly seen around the world. In Australia, they would have swells coming from the Southern Ocean interacting with the wind sea, which are a local phenomenon. You see this sort of bidirectional condition in Brazil as well. So bidirectionality is defined as when the swell, which is more predictable, comes from a certain direction, and then the wind sea, which is a locally generated condition, can change direction relative to the swell. So we assumed our FPSO is operating in one of these conditions, and it's oriented in the direction of swell, and then when the wind is applied, wind sea is applied, what sort of movement is this platform going to have? Will it be will it weather vane in the swell direction, or will it change towards the wind sea, or what will it do? And what we found was something very interesting. So you see the y-axis is the heading angle of the hull. X-axis is not the wavelength anymore, it's the wind sea direction. And this is the 45, the black line is a 45-degree line, and our experiments show, which is shown by the red dots, show that the heading angle of the hull is about half. So it's in between the swell and the wind sea, kind of aligning itself somewhere there. Whereas our numerical simulations, which we did, showed that the vessel should orient itself in the direction of the wind sea. So there was clearly a very large discrepancy between what we are seeing in the case of our numerical simulations versus what we are seeing in the experiments. And then we said, okay, what can we do? What we started understanding was, when you have two wave systems coming in two different directions, you have the wave numbers of these two, and wave number is a vector, right? So you look at the difference between the two vectors as well. So that is, the second order potential of this combined wave system creates something called a bound wave. And this bound wave actually has a wave number which exactly matches this difference vector between the two wave number vectors. So when we do simulation with bidirectional sea states, we don't just input the two sea states, we actually have to input a third sea state, a third component of the sea state, which is this bound wave. So previously, when we did simulation, we only had the swell and we had the sea. And that's typical of simulations we would do in the industry. Now, what's often ignored is this component, which is this bound wave given by this the difference between these two. And the interesting part of this is because the waves are directionally separated, so this is a relatively less known correction phenomenon, which have not been used before. So once we add this third component and then we do our simulation, what we find is, lo and behold, our simulations match very well with the experiment. And if you need some more details, you can look at our paper in Applied Ocean Research from 2018. So in here, in the part one of my talk, what I've shown is how the conventional mooring system, how it has been designed, deployed, tested, and how it had contributed mainly to the horizontal plane motions. And what we were talking about is yaw motion and yaw instability and equilibrium of a vessel in the yaw motion. Now, what we have been seeing in the industry is, as we have progressively been moving into more challenging mooring arrangements, we are finding more and more failures in the mooring systems. And recently I've been looking at some literature where people have documented failures among the installations, floating installations in the Gulf of Mexico. There's been quite a few among the reported failures. Some of them have requiring a shutdown of the installation and of the production. It results in a very high probability of failure, an annual probability of around 0.3%, which is quite considerable and significant. So when you do mooring designs, you really think about a very low probability of failure, and having large reported failures kind of results in people thinking whether the standards we have, the guidelines we have, and the design practice we have, are they adequate enough? And this is only compounded further when we take all that mooring and the designing and the analysis ideas into an emerging industry like offshore wind. So let's look at what actually happens to a mooring system when we have waves. So a floating platform basically responds to waves, and it has, we characterize the response by the response amplitude operators, right? And when the vessel is moored, the motion has the various components, which is the mean offset and the wave frequency motion, and the natural frequency motion, often called the slow drift motion for oil and gas platforms like spars, FPSOs, and semis. So in the oil and gas world, these three motions are, like I was saying, they are in a frequency spectrum, they are kind of segregated. So you have the mean motion, and then you have the slow drift motion given in the red curve, and then you have the wave frequency motion, which acts on top of this, on top of the slow frequency motion. Now, as we get into more complicated mooring systems, what we are finding is the mooring tensions are affected by these very large wave frequency motions, resulting in rather large tension variations, maybe one of the reasons for the failures we are seeing. So when we look at offshore wind turbines, like I was contrasting with oil and gas and deepwater installations, the mooring basically does not interact at the wave frequency. And because the slow drift loads are much smaller in magnitude, you can get away with the smaller mooring cross-section and a typical mooring line that's been used before. But when we get into floating offshore wind turbines, we are moving into shallower waters. The platforms have lighter displacement. That results in some complications. And we are also customizing technology quite rapidly, which is a social aspect of this problem. What we together see is mooring is affected by wave frequency. And so when the mooring is also moving and the platform is moving, you could end up in points where something called a slack snap phenomena, which is basically a shock load that can also transmit. So mooring lines are now affected not only by the wave frequency motions, we can also see shock loads that could occur in these mooring lines when applied to offshore wind turbines. To investigate whether this thing is true, we resorted to an experimental data set, which was a DOE-funded research program that was conducted by the University of Maine and a consortium. They tested three generic platforms: a spar, a semi-submersible, a 3-column semi-submersible, and a tension leg platform, all carrying the same wind turbine. And this was tested at the Marin facility in the Netherlands. So it's a 1/50th scale experiment, and a number of papers have been published on this data set. So what we did, we took the data for the semi-submersible, and we were looking at the 3 mooring lines for the semi, and we wanted to see what sort of tension variation we get in the semi. What you see here is a numerical simulation in Orcaflex, but we also, what I'm going to show you in this talk is basically experimental data sets. So in the experiments, they had mooring lines, which are basically steel wires with the little springs at the end to get the right tension offset curve to match with the prototype. And this wasn't in very shallow water. It was quite deep, like 200 meters is the kind of the target water depth for that set of experiments. But even in this case, I will show you there are some very interesting mooring dynamics issues. So we took 7 test cases from a number of experiments they did. And you can see the significant wave height here, 10.5 meters, the peak period, 14.3 seconds. So it's corresponding to an extreme event, like a 50 or a 100, it's actually a 100-year event. And then you have wind conditions, a range of wind conditions, starting from dynamic conditions, steady conditions, no wind with the different wind speeds. And if you look at the tension in the 3 lines, so line number 1 is the one which is in the direction of the waves and the wind. The wind and the waves are coming from left to right. 2 and 3 are the downstream mooring lines. And what you find is in the graph below, you see these dark red lines are basically the tension. The y-axis is the tension in full-scale units in kilonewtons and versus time. And what we find is the downstream lines have a tension which is very close to the static tension, the pre-tension value. But you see in line number 1, which is the upstream line, encounters quite significant movements in its tension, and in some cases quite sharp, very large peaks in the tension. So we took the data for line number 1, and then we analyzed it to see if any of them might be what are called snap loads. Snap loads occur when a line momentarily goes slack and then it picks up. So it's very similar to how we would, at home, we would just break a piece of rope. You just slacken the rope, and then you pull it tight, the rope splits, and that's a much easier way to break the rope. And the same thing happens in some of these mooring lines. The mooring line, what we saw in line number 1 is the line goes slack at several points or very close to being slack. It's a 10% allowance is given. So 0 is the slack condition. There is a 10% of the pre-tension value, which is the red line. So we are very close to being totally slack, and then we see that the line picks up rapidly and then gets into a very large, very spiky tension value. So we looked at every one of these oscillating cycles, and then we categorized them into snap conditions and the non-snap condition. A non-snap condition is where the minimum tension does not get very close to 0. And then we grouped them, and we looked at, for each of those cases we studied, we looked at what is the tension range. All the numbers you see here are in terms of the RMS tension. And out of the total number of cycles of close to 1,000, we are getting about 20 to 30 or 20 to 40 snap conditions. The snap was characterized, as you can see here, by very high maximum tensions. And the non-snap, you can see relatively it's about half of this tension. So we said, okay, what does this all mean? Can this be ignored like it's currently being done? Or is there something else we can do? So we looked at some exceedance probability of the data we have. And when we plot the exceedance probability in the y-axis versus the tension value, what we find is all the smaller values of tension kind of align themselves quite nicely. And then the real extreme values are primarily due to the snap conditions, which are just shock loads in the line. And we said, okay, what more can we understand? Can we fit a probability model? Can we make sense of it? If you take your standard Weibull probability model and you fit it into it, and what we find is it fits the lower end quite well, and then it just drops off. So it considerably underpredicts the extreme tension value. So we used the usual maximum likelihood estimate, and what we found was that we are considerably underpredicting the probability of extreme values. So we said, can we somehow fix it? And we resorted to some of the models which were actually proposed for wave breaking, and how we can look at the wave heights before and after breaking. And there are some papers looking at what are called a composite curve. So you have one set of parameters for the curve before breaking and another one for after breaking. So we said, okay, can we do something similar? And we proposed a composite Weibull model for one set of parameters before a critical tension, and one set after the critical tension. And what is that critical tension? It's a transition point that goes from the non-snap to the snap event. How do we characterize this transition? And that became pretty obvious when we looked at this curve, and we segregated the non-snap, which is shown by the red data, and the snap, which is the green data. We'll ignore that for the time being. You see, the blue data is a total all the tension measurements. So we clearly see that the point where the non-snap deviates from the blue curve, which is a total data, could easily be designated as a transition point. And so we said, can we take our standard Weibull curve and then predict what this maximum tension as predicted by the standard Weibull is, based on the data sets we had, and then define the transition tension simply based on the maximum tension we got from the Weibull curve. And that's all we did was take the maximum tension and then normalize it to suit our notation, our convention here. And once we do that, we find that our composite distribution has a Weibull curve up to this point, and then it has a little kink there, and then you have a second Weibull, which seems to capture the way this snap loading has happened. And this actually was presented in a marine structures paper from a couple of years ago. What's very interesting is with this, can we make some sense out of it? We can look at the most probable maximum value of the tension. If we just use the Weibull curve without any of this correction for the snap, we find that the Weibull predictions are quite a bit lower than this composite Weibull prediction, which gives you results which are very close to what we saw in the experiment. So if you take that and then translate it into a safety factor principle, so DNV's formula for predicting the tension and the safety in a mooring line is you have the mean tension and the dynamic tension. Each of them have a partial safety factor, gamma mean and gamma dynamic. All of this combined should be less than a characteristic strength of the rope, which is very close to the mean breaking point. So when we include our composite Y-bolt, we find that we actually, using the composite Y-bolt, and we calculate this, the safety factor here, we are getting, actually the tensions are higher compared to the tensions from which DNV is using. And you see this ratio is about 2.7. So if you are using the traditional design approach and ignoring the snap, then you simply have to accommodate this increase in tension in the safety factor. So we are, our conclusion was the safety factor for dynamic tension could easily be increased by 2 to 3 times in some of these novel applications. My student, Waiting Shu, who took this one step further, she also looked at it from a numerical analysis standpoint, and she tried to predict the tensions from well-known software, Arcoflex. And she found that this ratio of 2.8, 2.7 to 2.8 was lower, somewhat like 1.8 to 2 in the numerical simulations, considerably lower than in the experiment. So we don't know if it's because the experiment was kind of, they had a mooring system was somehow showing something very, something which is not really seen in reality, or is the simulation missing out on something which we should be considering. So it was an open-ended question, and that kind of brought us to our current work on synthetic lines. And I see I'm close to running out of time here. So I'll quickly run through what we are doing here and how it relates to what I just showed you. We had, this is aquaculture. So we worked with a couple of aquaculture farmers in Maine. This is an oyster farm. And we instrumented a bunch of lines in an oyster farm. So we instrumented some of the mooring lines, and we measured the tension in the lines. We also measured the tidal variations and the environment. And this is what we saw. We find, you see two sets of lines, the inner line and the midline, and you see the mooring tension is on the orange color. And the lower set of data is the current versus the current, and the upper set is versus the tidal elevation. So the oscillating curve here is the tidal radiation at that location. The lower part relates to the current at the same instant of time at that same location. And it's kind of very apparent in the top right figure. What you see there is the mooring line, the tension. It has a large range of kind of a very slack condition. And so it doesn't follow the tide exactly. In fact, it has a tendency to drop off rather rapidly while the tide is still slowing down. And so that was very interesting to us. And this became even more apparent when we also instrumented a long line system. Also in the same neighborhood, we instrumented a couple of the long lines which carried kelp, growing kelp at that time. And what we found was also, I'll skip this figure and show you this one. And here you can see also the line tension, which is shown by the blue line at the top. Has this tendency to drop off suddenly while the tide is still changing. The tension is actually well aligned with the currents, but you can see there is this sudden drop there. And we believe that's due to the viscoelastic and viscoplastic nature of the synthetic lines. I'm going to skip this and show you this. So right now, what we are looking at is a nonlinear model for the mooring system, which comprises of a viscoelastic and a viscoplastic constitutive equations, which are both time dependent. Some of them are recoverable, the elastic nature, which is what we saw in the orange and the blue curves there. But the viscoplastic is, of course, a permanent, non-recoverable deformation. So we have currently completed a validation work of a mooring line simulation model. As you can see here, there is a line with connecting a fair lead to an anchor, and there are some measured data for that line, and our simulation result shown in red matches the tension as was measured quite well, which shows actually the viscoelastic behavior in between all these rise and fall. We can also capture the hysteresis loops, which is when you load the line and you unload the line, you see very different stress lines. So we can take all these and then look at how the stress translates into strain and how the line gets slack because of the extended strain, and how it can combine together when you have sudden rapid changes, like when you have wave loads and when you have a slack and a sudden, like a snap condition. So our current work, which is my last slide, is how we can integrate this viscoelastic and viscoplastic models into a CFD and the numerical similar prediction tools. And we are currently working on getting some experimental data and validation. So rather rushed, but I hope I gave you an idea of how mooring line kind of runs as a common thread, no pun intended, across all these areas we are working on, and how many of these you can really move from one area to the other, whether it's oil and gas, wind, or aquaculture system. Thank you.